Good morning, students. Welcome to video lecturing class for the subject Dynamics of Machines. So, in the last class, we have discussed about the basics of force vibration, the undamped single degree of freedom system, and the damped single degree of freedom system, which is under the forced vibration. Also, we have studied about the magnification factor. So, today we will continue the discussion on the concept of frequency response. So here the concept of this frequency response curve, basically it is obtained if the constant force, that is applied force F at a variable frequency, is applied to the system. So now there are two concepts which you need to understand for this frequency response. The first one is rotating unbalance. Okay. So here, if a machine is having the rotor as one of its components, is called as rotating machine. Like turbines, IC engines, you can call them as the rotating machines. And the unbalance in rotating machine is common source of vibration excitation. The unbalance occurs when the center of gravity, that is CG of the rotor, does not coincide with the axis of rotation. So let us consider a system comprising of a spring mass damper, which is considered to move in the vertical direction and excited by a rotating machine that is in the unbalanced condition. It is shown in this figure here. Okay. Yeah. So here the unbalance is represented by an eccentric mass m with eccentricity e, which is rotating with an angular velocity omega. So let m, that is capital M, be the mass of the machine including mass m, and x be the displacement of the non-rotating mass, that is m minus n. So now the displacement of mass m is given by x plus e into sine omega t. Okay. Therefore, the equation of motion for the given system, we can write it as m minus m into x double dot. That is, we used to write mx double dot, but here the non-rotating mass is m minus m plus m into d square by dt square into x plus e into sine omega t. This is also mx double dot only. Okay. So in place of x, we are substituting this displacement value. Okay. Equal to minus kx minus cx dot. Okay. So now, if you see that equation, if you simplify that equation, it will be minus mx double dot mx double dot minus mx double dot plus mx double dot minus m omega square into e sine omega t minus kx minus cx dot. So here to get this one, you have to differentiate twice this term. Okay. So we will get the equation as mx double dot plus cx dot plus kx equal to m into omega square into e into sine of omega t. So comparing this equation with mx double dot plus cx dot plus kx equal to f naught sine omega t, which is standard differential equation for the forced vibration. Comparing with this standard equation, so we can write the equation as x max as m into omega square into e divided by root of k minus m omega square whole square plus c omega square, which can be written as e into omega by omega n whole square divided by the root of 1 minus omega by omega n square whole square plus 2 zeta into omega by omega n whole square. Okay. So similarly, we can write the phase angle phi as tan inverse of 2 zeta into omega by omega n divided by 1 minus omega by omega n whole square. So to make x by e as a non-dimensional term, so we can multiply that equation number 2 by m by m. So if we multiply that equation by m, we get the equation as x max as m by m into e into omega by omega n whole square divided by under root of 1 minus omega by omega n whole square plus 2 zeta into omega by omega n whole square. So the complete solution of for that equation we can write it as x of t as xc plus xp. So x of t is nothing but x into e raised to minus zeta into omega nt sine of omega dt plus pi 1 plus xp as m into omega square into e into sine of omega t minus pi divided by root of k minus m omega square whole square minus c omega square. So the next one is the reciprocating unbalance. So in this reciprocating unbalance, the figure B shows the reciprocating engine. This is for reciprocating engine and this is for the rotary unbalanced system. So let M be the equivalent mass of the reciprocating parts and capital M be the total mass including M, and L be the length of the connecting rod, and R or equal to E equal to length of the crank. Inertia force due to the reciprocating mass, it is M, is given by M into omega square into E into sine of omega t plus E by L sine of 2 omega t. Since E is small here, so the second harmonic force can be neglected. So we can write directly the exciting force as M into omega square into E sine of omega t. So now moving further, the next concept is vibration isolation and the transmissibility ratio. So the main vibration isolation, in case of vibration isolation, the vibratory forces generated by the machines are often unavoidable and their effects on the dynamic system can be minimized by the proper isolator design. So an isolation system attempts either to protect a delicate object from the excessive vibration transmitted to it from its supporting structure or to prevent the vibrating forces which are generated by the machines from being transmitted to its surroundings. So therefore, the effectiveness of isolations may be measured either in terms of force or motion. So the first type is known as the force isolation, where the second type is known as motion isolation. So lesser the force or motion is transmitted and the greater the isolation. So there are some commonly used isolation materials are like rubber, cork, felt, pad, metallic, springs. Okay. So in these, the rubber is suitable for the shear loads and cork is suitable for the compressive loads, and all these isolation materials are elastic and possesses the damping properties. If they do not possess the damping properties or if they are not elastic, we cannot use them as the isolators, because the main concept of isolation is nothing but is to reduce the vibration, or it is to absorb the vibration, or it is absorb the motion which is transmitted to from the machine. Okay. Next concept is transmissibility. So it is the ratio of force transmitted to the foundation to the impressed force is known as transmissibility. So normally it is denoted by TR. So the vector diagram for this shows the forces acting on the mass under this steady state condition. So out of these four forces, this is the vector diagram. Only the spring force Kx and the damping force C omega x will act on the mass as well as on the foundation. So therefore, the force transmitted to the foundation is the vector sum of these two forces, that is spring force and damping force, and it acts in the direction opposite to the mass. So the force transmitted to the foundation, that is Ft, can be written as under root of kx square plus c omega x square from this vector diagram. So x is common, and take x as common term, so it is a root of k square plus c square into omega square. Or I can write the x max as x equal to f by k divided by 1 under root of 1 minus r square whole square plus 2 zeta r whole square, where r is omega by omega n. and Ft is F by K divided by 1 minus under root of 1 minus r square whole square plus 2 zeta r whole square into root of k square plus c square into omega square. So therefore the transmissibility ratio, that is Ft by F naught, is given by, where this F naught is m into omega square into A. Transmissibility ratio is given by under root of 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square. So from the vector diagram, the angle through which the transmitted force lags the impressed force can be determined, that is pi minus alpha. So where this alpha is given by tan inverse of c omega x divided by kx, or tan inverse of 2 zeta into omega divided by omega n. So pi minus alpha can be given by tan inverse of 2 zeta r divided by 1 minus r square minus the alpha value is tan inverse of 2 zeta r, where this r is omega by omega n. Okay. So now this figure shows the plots of the transmissibility ratio against the frequency ratio, that is omega by omega n, for the various values of damping factor. And in this figure you can observe that when omega by omega n is greater than root 2, the transmissibility ratio is more than 1. That is, transmitted force is more than the exciting force. The second case is when omega by omega n is greater than root 2, that is less than 1, the transmitted force is less than impressed force. When omega by omega n is equal to root 2, the transmitted ratio is equal to 1. Therefore, the transmitted force is equal to impressed force. When omega by omega n equal to 1, that time the transmitted ratio will be infinity. That is, the transmitted force is infinite in nature. So therefore, for all the values of omega by omega n greater than root 2, the transmitted force is less than the impressed force. Therefore, the vibration isolation is possible only in the range of omega by omega n is greater than root 2, which you can observe from this graph. Only up to here the vibration isolation is possible. Okay. Now moving further, the support motion or the base excitation. So most of the mechanical systems are mounted on a moving support or the base. So if you take the case of locomotives or the vehicles, the wheels act as a support or a base for the system. So therefore, the motion of the support or the base causes the forces to be transmitted to the mounting equipment. So here in this figure, it will show you the single degree of freedom spring mass damper system with a moving support or the base here. Okay. So in many cases, the excitation of the system is through the support of the base instead of being applied to the mass. So you can assume that the support be excited by a regular harmonic motion. That is y as y sin omega t and y dot as capital Y into omega into cos of omega t. So in that we have two concepts. One is absolute motion. So here the motion of a mass with respect to the coordinate system attached to the earth. That is the motion of the mass with respect to the coordinator system attached to the earth is called as absolute motion of the mass. So now for this, let the x be the absolute displacement of mass, the displacement of mass m relative to the support z, and the net elongation of the spring is x minus y. Okay. and the relative motion between the two ends of the damper is x dot minus y dot. So now we can say that z as x minus y, z dot as x dot minus y dot. So this equation of motion can written as mx double dot plus c into x dot minus y dot plus k into x minus y equal to 0. Okay. So if you simplify that, you get this equation mx double dot plus cx dot plus kx equal to cy dot plus ky, where this, if I take y as common, left with k into sine of omega t plus c omega into sine of omega t. So I am substituting y as y sine omega t, y dot as y into omega into cos of omega t. Substituting, then if you take y as common, you will get this equation, and this can rewrite the equation as y into under root of k square plus c square omega square into sine of omega t plus alpha, where this alpha is tan inverse of c omega by k, which is equal to tan inverse of 2 zeta into omega by omega. But we have the standard equation, differential equation for the force vibration, mx double dot plus cx dot plus kx equal to f naught sine omega t. So comparing this with that equation number A, the steady state solution can be written as x into sine of omega t plus alpha minus phi, where this x can be written as x equal to y into root of k square plus c omega whole square divided by the root of k minus m omega square whole square plus c omega whole square. Therefore, if you substitute those values, that is wherever k and c omega is there, if you simplify that one, you will get the equation as x by y as 1 plus 2 zeta r whole square divided by 1 minus r square plus 2 zeta r whole square. So here, if you take this is also under root for both the numerator and the denominator. If you forgotten to write this root for this numerator, so please make a note of that. Then pi is given by tan inverse of 2 zeta r divided by 1 minus r square, and the phase angle is pi minus alpha. So in place of pi, you substitute the equation, and in place of alpha, it is minus tan inverse of 2 zeta into r. Then the second one is relative motion. If the z is the relative motion of the mass with respect to the support, then we can write z as x minus y or x as y plus z. So if you substitute this in equation number 1, you will get it as mz double dot plus cz dot plus kz equal to my double dot. So where y is y sine omega t. Again, for the steady state amplitude, if you simplify that, you will get z equal to y into r square divided by 1 minus under root of 1 minus r square whole square plus 2 zeta r whole square. And the pi is tan inverse of 2 zeta r divided by 1 minus r square, where this z by y is called relative displacement transmissibility. Okay. So here today we have discussed about concept of frequency response. In that we have two bits, that is rotating balance and reciprocating unbalance. So that the vibration isolation and the equation for the transmissibility ratio and the base excitation. Okay, so in that we are having absolute motion and relative motion. So for these concepts, in the exam you may get the theory questions on these concepts, that is explain the base excitation or support excitation for absolute motion or relative motion. So in such cases you need to give the explanation along with these equations, and you have to remember all these equations to solve the problems. Okay, and similarly you may get the question on write a note on vibration isolation or the transmissibility ratio. That time you have to write the definitions and you have to draw those vector diagrams, and along with that you have to write the equations for that transmissibility ratio. And for the concept of frequency response, you may get the rotating or reciprocating unbalance theory question. So that time also you have to explain the things and then you have to write the relative equations. Okay. So just go through this video and the previous class, and in both the class whatever the equations we have derived at the end, you have to remember those equations to solve the problems. So with this we'll conclude the today's session here itself. So in the next class we'll start with the problems. If you have any doubt you can leave the comment in the comment box. Thank you.